Welcome to the Deep Dive, where we plunge into the cutting edge of research to extract the most important insights for you. We've all seen the incredible leaps large language models have made. Writing code, holding surprisingly nuanced conversations.
It's been amazing progress.
Absolutely. But for all their power, the quest continues.
Yeah.
How do we make them even smarter, more reliable, maybe capable of truly independent thought?
That's the million-dollar question.
We usually hear about AI that learns from humans,
Yeah.
examples, or from clear, verifiable answers. But what if an AI could learn and improve simply by trusting its own gut? How much of a departure is that from what we're used to?
Oh, it's a huge philosophical and practical leap, actually. Up until now, almost every successful AI system has relied on some form of explicit external feedback.
Right, someone or something saying good job or try again.
Exactly. Whether from humans or predefined rules, the very idea of internal self-correction, well, it opens up a whole new set of challenges and opportunities that we're only just beginning to grasp.
And that's what we're exploring today. We're taking a deep dive into a fascinating new paradigm called reinforcement learning from internal feedback, or RLAF.
RLIF, yeah.
Our mission is to unpack a groundbreaking method within this called Intuitor. We'll explore how it allows language models to enhance their reasoning abilities using nothing but their own internal confidence.
Just confidence. It sounds almost too simple.
Doesn't it? But you'll see how this approach tackles some of the biggest challenges in AI training, offering maybe a scalable path towards truly autonomous learning systems.
And all of our insights for this deep dive come directly from a recent research paper, Learning to Reason Without External Rewards, and its figures. So it's pretty fresh stuff.
Fresh off the press. Okay, so to really get the significance of this new idea, RLAF, we first need to quickly revisit the foundation. How have LLMs typically learned, and where do those methods, get stuck?
Right, context is key.
For years, AI has faced this fundamental challenge. How to truly learn without constant hand-holding, right? Our journey today starts by looking at the conventional approaches that have pushed the boundaries.
Okay.
Many of us are familiar with reinforcement learning from human feedback, RLHF. It's been absolutely crucial for aligning LLM outputs with, well, human values.
Indeed. And the main benefit there is pretty clear. RLHF enables models to understand and reflect human preferences. Makes them safer, more useful in practice.
But it's not perfect.
Definitely not. There's a significant limitation.
Yes.
It's incredibly costly, all that human annotation.
Hours and hours of people rating outputs.
Exactly. Which also introduces human biases, naturally. And it's very resource intensive to maintain, especially at scale.
So RLHF is about aligning the AI with us, but cost and bias are big hurdles. How does reinforcement learning with verifiable rewards, RLVR, try to fix that?
Well, RLVR emerged as an alternative. It basically replaces the human feedback part with automatically verifiable signals.
Okay, so machines checking machines.
Sort of. It's very effective for tasks where there's a clear right or wrong answer, like math problems or code generation. DeepSeek R1 is a great example of a model using this approach really successfully. Impressive results.
Right, but this is where the limitations of even RLVR become really clear, isn't it? Even with RLVR, you still need these domain-specific verifiers, these gold standard solutions.
Precisely. You're talking expert annotated math solutions or really comprehensive test suites for code, things that are themselves hard to create.
So this reliance on perfectly correct external answers, it feels like a fundamental bottleneck. It limits how broadly you can apply it, doesn't it?
It really does. The paper actually flags this as a critical research question. Can we move beyond needing an external expert or a perfect answer key for every single step of learning?
And that leads us right to the big shift.
Exactly. This is where we see a significant paradigm shift with reinforcement learning from internal feedback, or RLIF.
RLIF. So the core innovation here is no external evaluation.
Correct. Instead of relying on external feedback, human or rules, RLIF uses the model's own assessment of its outputs, or even its reasoning process. That's the feedback.
Wow. Okay, the implications there seem pretty profound.
They are. It drastically reduces reliance on that expensive supervision infrastructure we talked about.
No more armies of human labelers, potentially.
Potentially. And it provides task-agnostic reward signals. Plus, critically, it supports learning in domains where external verification might just be impossible or unavailable.
Especially thinking ahead, as models get closer to or maybe even better than humans at certain tasks, how would we even verify them then?
That's the point. This ability to learn without a human or a perfect verifier in the loop becomes absolutely essential.
So the big idea Just to boil it down, imagine an LLM improving itself. Not because someone tells it it's right or wrong, but because it gets more certain of its own internal reasoning.
That's the essence of it. It's truly a form of self-improvement. Like, it has an inner voice guiding its own learning process. It's learning to trust its gut, essentially.
An inner voice for AI. That's quite a concept. And that radical shift leads us directly to the method at the heart of today's deep dive. Intuitor.
Right. Intuitor.
This novel RLIF method basically operationalizes this learning from within. It uses the model's own confidence as its sole intrinsic reward.
And what's fascinating here is how they define that self-certainty. It's not just a vague feeling.
Okay, how do they measure it then?
Think of it like this. If a model is extremely confident about the next word it's going to generate, its internal prediction will be very sharply focused on that one word.
As opposed to being spread out like it's unsure between several options.
Exactly. It's not spread out vaguely across many possibilities. This sharpness or concentration in its predictions is what they measure using a concept from information theory called KL divergence.
KL divergence, okay.
The more focused the prediction, the lower the divergence from a single point. Or rather, the higher the divergence from a uniform, uncertain distribution, the higher the self-certainty score. And this higher score indicates greater confidence.
And this confidence correlates with actually being correct.
That's the key observation, yes. Higher self-certainty has been observed to correlate strongly with correctness in many cases.
So how does rewarding this increased self-confidence actually guide the learning? It sounds, well, more nuanced than just yes or no.
It is more nuanced. By rewarding increased self-confidence, Intuitor encourages the model to iteratively practice and refine its reasoning pathways. It keeps trying until it becomes more confident in its outputs.
So it's not just guessing better, it's changing how it gets to the answer.
Exactly. It involves modifying the generation process itself to build that conviction. It encourages more deliberate, more refined thought processes internally.
And the implementation. Is it complicated to set up?
Surprisingly, no. It's quite elegant in its simplicity, actually. Intuitor just replaces the external reward signal that you'd normally use in these reinforcement learning setups.
Like RLHF or RLVR setups?
Right. Specifically, they mention using it within a method called Group Relative Policy Optimization, or GRPO. That's just one of the standard ways AI models learn from feedback.
Okay.
But importantly, Intuitor swaps out that external feedback, that external reward, for these internal self-certainty scores. All it needs is a clear prompt to start with. No verifiable reward, no human feedback.
Just the prompt and its own confidence metric. That's it.
A core idea.
Okay, theory sounds good.
Yeah.
But the real test, of course, is in the experiments.
Right.
What did they find? They trained some Qwen models, right?
They did. They trained Qwen 2.5 1.5b and Qwen 2.5 3b models on the math dataset, and they compared Intuitor directly against GRPO, which uses the traditional approach with golden answers.
The answer key method.
Exactly. And they also created an Intuitor code variant they tested on the Codeforces dataset for coding tasks.
So math and code, what were the standout results?
Well, the performance highlights are quite remarkable. First, big insight on the math benchmarks, things like GSM-8K and Math 500. Intuitor actually matches GRPO's performance.
Matches it. But GRPO uses the correct answers.
That's the revolutionary part. Intuitor gets there without ever seeing a single correct answer. Imagine. It's like an AI learning advanced math without a teacher ever marking its homework, just by becoming more sure of its steps.
That's a powerful difference. Learning without the external answer key. And you mentioned generalization. That seems critical for real-world AI.
Absolutely critical. And this is where Intuitor really shines. For one of the models, the Qwen 2.5 TB trained only on math problems.
Okay.
Intuitor resulted in a huge 65% relative improvement on a code generation task, Live Code Bench, and a 76% gain on another reasoning benchmark, CRU X Evaldo.
Whoa. So training on math improved its coding and general reasoning that much, just from self-confidence training.
Exactly. Now, contrast that with the standard GRPO method, trained on the same math data but with answers. It showed little to no improvement on these out-of-domain tasks.
So GRPO learned the math, but couldn't really transfer it. Intuitor learned the math and somehow learned more general reasoning skills.
That's what the results suggest. It highlights Intuitor's exceptional ability to transfer knowledge, or perhaps reasoning processes, to entirely new, unseen domains.
And there was an even more striking example with the smaller model, right? The 1.5B parameter one.
Oh yeah, that one's fascinating. That Quen 2.5 1.5B model, before tuning, it was basically outputting repetitive nonsense, gibberish. It scored 0% on that live code bench coding task.
0%. Okay.
After intuitor tuning, again, only on the math dataset, it learned to emit coherent reasoning chains and well-structured code. It reached nearly 10% accuracy on live code bench.
From 0 to 10% on coding just by practicing math problems using its own confidence.
Yep. This isn't just a small tweak. It's like it learned how to reason more effectively, and that skill transferred. It's a fundamental leap in its ability to generalize without explicit training on code.
That's incredible. And it wasn't just about getting answers right, was it? It also got better at following instructions.
That's right. They saw significant improvements in instruction following. On the Alpha-Keval benchmark, they saw a higher length control win rate, basically. It got better at generating responses of a requested length. It produced less gibberish.
Fewer nonsensical outputs.
Right. And just showed robust gains in actually adhering to the instructions it was given.
And what about the reasoning process itself? Did they see differences there?
Yes. And this is really interesting. Intuitor consistently outperformed GRPO in the early stages of training.
Faster learning initially.
It suggests a more effective learning trajectory right from the start. Possibly because its reward signal, the self-certainty is continuous and aware of the whole reasoning process, not just the final answer.
Makes a constant signal versus just a final grade.
And here's something else cool. Models trained with Intuitor started showing spontaneous structured reasoning before they even generated the final answer or code.
Like thinking out loud first.
Kind of. For example, on that CRU Exivalo task, the models would often exhibit this free-form reasoning, like explaining their plan, before summarizing it in the required JSON format.
Okay.
Or on the coding task, live code bench, they'd provide natural language reasoning before writing the code.
So reinforcing confidence encouraged them to build these more elaborate, self-explanatory thought processes.
That's the hypothesis. It seems to create a more robust, more understandable reasoning process within the model itself. It's not just a black box anymore, it's showing its work.
So you see models first learning to generate, say, valid code. And then they actually develop this pre-code reasoning, almost to convince themselves the code is right.
Exactly. And that internal convincing process, driven by the search for higher self-certainty, seems to lead directly to improved accuracy. It's a fundamentally different way of learning, building internal justification.
Okay, this sounds really promising, but it raises a flag for me. What about reward hacking, that classic problem in reinforcement learning where models learn to exploit the system?
Ah, yes. Good question. That's a real danger.
We've seen it before, right? Models artificially inflating scores, maybe by appending answers to easy solved problems onto their actual answer, just to gain the reward.
Exactly. That can lead to ridiculously long responses and often a total collapse in actual accuracy. They look good according to the metric, but they're useless.
So how does Intuitor avoid this? Especially if it's just rewarding confidence. Couldn't a model just become confidently wrong? Or find some trick to boost confidence unnaturally?
That's where the online nature of the self-certainty reward comes in. It's not a static target.
What do you mean by online?
It means the reward signal, the self-certainty calculation, co-evolves with the policy, with the model itself as it learns. The target is always moving based on the model's current state.
Ah, so it can't just find one simple trick and exploit it forever because the definition of high confidence is adapting as the model improves.
Precisely. This dynamic reward successfully prevents that kind of reward exploitation or hacking. The system maintains stable training dynamics. It's much harder to game a moving target.
Okay, that makes sense. And is there evidence for this robustness?
Yes, the paper shows that policies trained with this online self-certainty actually get better at discriminating between their own correct and incorrect answers, even while their overall confidence level might be going up.
So they become more confident overall, but also better calibrated, more confident on the right answers, and less confident on the wrong ones.
Exactly. Which makes Intuitor quite robust against those common exploitation strategies.
That's crucial. Now, looking ahead, are there other important details or nuances here? You mentioned KL divergence earlier.
Right. The KL penalty they use alongside the reward is actually quite important. It acts as a critical regularization mechanism.
Regularization, like keeping the model from going too far off track.
Essentially, yes. Think of it as a guardrail. It prevents the model from drifting too far from its original knowledge base during this intense self-improvement training. It stops it from forgetting what it already knew or just degenerating into something weird.
And that helps with generalization, presumably.
Crucial for robust generalization across different domains, yes. It keeps the learning grounded.
Okay. And what about scaling this up? The experiments used, well, relatively smaller models by today's standards. Does this work for the giant foundation models?
That's a key next step. The paper suggests the potential for Intuitor in much larger models is significant, but it might require some tweaks. Maybe hybrid online, offline schedules, things like that.
So more research needed there, but the core principle seems applicable.
Seems so. And they also point out that this Intuitor framework, using self-certainty as a reward, isn't necessarily tied only to that GRPO algorithm they used.
Oh.
It suggests the framework is flexible. You could potentially plug this self-certainty reward into other common AI learning methods, other policy gradient algorithms like Reinforce or PPO.
So it's a more general concept?
Potentially, yes. And looking even further ahead, there's immense potential for maybe combining these intrinsic rewards like self-certainty.
With the external methods we talked about earlier, like RLHF or RLVR.
Exactly. You could imagine hybrid approaches. Maybe using self-certainty for broad reasoning improvements and then fine-tuning with human feedback for specific alignment goals. Leveraging the strengths of both internal and external guidance.
Best of both worlds.
That could achieve even greater capabilities across various dimensions for these AI systems.
So if we connect this back to the bigger picture,
Yeah.
what does this push towards internal feedback really mean?
Well, it suggests a plausible path toward truly autonomous AI systems that can learn and improve in domains where human supervision or explicit correctness metrics just aren't available or maybe aren't even feasible.
Places where we don't have the answers ourselves.
Right. Or where the complexity is just too high for external verification.
So wrapping this up, what does this all mean for you listening in? Today, we've explored Intuitor. It's a groundbreaking method, really. It allows these large language models to learn and improve reasoning, instruction following, just by assessing their own confidence.
Yeah, it's a significant step beyond relying solely on human feedback or those perfect, verifiable answers. It really opens up new frontiers for AI autonomy.
It truly does. It feels like it opens the door to AI agents capable of autonomous skill acquisition in areas that were previously inaccessible. It pushes the boundaries of what we thought was possible for self-improving AI.
Definitely a space to watch.
So here's a final thought to leave you with. Think about this. What are the implications for a future where AI systems can continuously learn and improve in totally new areas, maybe even surpassing human oversight, just by becoming more certain of their own understanding and output?
It's a huge question.
It really is. It's a provocative thought that challenges our current understanding of learning itself, and it signals perhaps a monumental shift in how AI will develop from here on out.